Okay, so I'm going to talk about one aspect of very simple linear algebra, which I probably should have told you early on, but I felt it was kind of very easy for you to work out, but I'll mention it nevertheless. In whatever we have been doing so far, whenever we talk about a matrix, we have what quality or property of it have we specified? Symmetric, positive, definite, right? So usually when I have a quadratic form like this, I say x transpose AX, where A is symmetric, positive, definite. Now, a very natural question which someone asked me a couple of classes ago was, why do we need this? Why do we need it to be symmetric? Supposing so what is the requirement for a positive definite matrix? How do I mean, what is the signature of a positive definite matrix? Eigenvalues are positive. Does that automatically imply that the matrix is symmetric? No reason whatsoever. But yet we say symmetric positive definite. In fact, all the books you read will say symmetric positive definite. Any idea why? Eigen decomposition will not change whether it's symmetric or asymmetric. It will be of use in analysis. That's one way of, that's one general hope. Any other? Eigenvectors are orthogonal. That doesn't really matter. So the real answer is that, pardon me? Yeah, we assumed A was symmetric, which means A transpose equal to A. Yeah, I'm saying why are we assuming that? So the gradient is more elegant. Okay, we will come to matters of elegance later. First, let's get the things set. Okay, so the answer is actually very simple. You can take A to be positive definite and not insist on it being symmetric. You know why? It doesn't matter. So let's see why it doesn't matter. So now let's start by assuming A is not symmetric, but we'll assume that it is positive definite. Okay, so what follows is very, very simple linear algebra. Can I write A in this form? Obvious, I just added and subtracted half of A transpose by, half of A transpose. But let's call this, let us say B, let's call this C. So can you say something about B? B obviously is symmetric because B transpose is B. Right? You can easily check that B transpose is equal to B. So this is called the symmetric part of A. What about C? Anti-symmetric or skew symmetric, because C transpose is equal to what? Minus C. So let's call this skew symmetric. So before we go ahead, what is the simple conclusion of this? Any matrix can be written as part symmetric, part skew symmetric. Okay. Now let us look at the action of, let's take up our quadratic form. Our quadratic form is x transpose AX. So x transpose AX. Obviously, I'm going to split that in terms of B and C. Fine. Now, x transpose AX, is it a scalar vector matrix? It's a scalar, right? So, for a scalar, if I put the transpose operation, what will happen? I'll get the same number back, right? So, if I do a transpose, that means that x transpose AX should be equal to x transpose AX, right? So, I am going to group these two guys together so that we can open up the transpose operation. So, therefore, this is going to be AX transpose X, right? AB transpose is B transpose A transpose. So X transpose, this is my first guy, and AX I flip the two. So AX transpose, X transpose transpose becomes X. So if I open this, this becomes X transpose A transpose X, right? So this is your hint in which direction it is going, right? So now I have this is equal to this. Let us substitute over here for A. So what am I going to get? On this side, when I substitute, X transpose AX is going to give me X transpose BX plus X transpose CX is equal to X transpose B transpose X plus X transpose C transpose X, right? So what else can we do? Is there any simplification that follows? What about X transpose BX? Can I cancel it? Right? Because B transpose is equal to B. What does this imply? And C transpose is minus C. So that leaves you with what? X transpose CX is equal to 0, right? So the action of the quadratic form, what does it do? It eliminates the skew symmetric component. So if X transpose CX is 0, this implies that X transpose AX is essentially X transpose BX, because X transpose CX is 0, right? So this is why, I mean, you see there's absolutely nothing fancy. We didn't even do an eigenvalue decomposition over here, right? So what is it telling you? That it doesn't matter if you add in the skew symmetric part. When I stick a X transpose X on both sides from left and right, it's going to knock off the skew symmetric part, right? So now we can come to the part of elegance which was stated earlier, that if you know this to be the case, may as well start working with a symmetric matrix in the first place itself, right? Because it's not going to matter. Is that clear? Very simple linear algebra. Okay, so the next part of, we're going to begin the next module of this course. We've finished line search methods, we have not finished line search methods, we have finished the gradient descent method, which is like your first algorithm for unconstrained optimization. And what was the basic premise in the gradient descent method was to walk in a direction of descent, right? Now this, you, in a first introduction to optimization, you would imagine that this is the most obvious thing. Go in the direction of descent, you're guaranteed to reduce the function value. And as we will see further on in this course, there are two non-intuitive ways of working with this. You say, okay, my search direction need not be a descent direction, I'll come up with some other clever criteria for it. And that gives rise to what is called the conjugate gradient method, okay? There is another version of this which gives rise to what is called as the accelerated gradient method. So we'll look at that later. Both of them question this idea of should I go in the direction of descent. Turns out you need not go in the direction of descent, but you come up with some other criteria and you're able to get good convergence. Okay, so that's why it's a very interesting way of looking at this problem. Okay. So conjugate so this is roughly chapter 5 of Nosedel, right, in case you are following along. Okay. Now what we'll do is, we'll introduce this again from a very simple case and then we'll begin to generalize it. In fact, this method has such a nice generalization that it gives you a way to work with nonlinear problems immediately. Okay, it need not be a quadratic form. But the motivation for this is as follows. In a lot of problems of engineering, whether it is mechanical, aerospace, electrical, you end up with a linear system of equations to solve, right? You will basically get system of equations of the form Ax is equal to B, and you want to solve this, okay? A and B can usually be extremely large, hundreds of thousands, millions, by million size, right? So your usual way of solving this when you took linear algebra would be what? Like LU decomposition, right? Which is called a direct method, which has a complexity of order n cube, right? So sometimes you're not willing to pay that price and you want a faster way of doing it. Now, having learnt optimization, how would you link it to solving this problem? This so far doesn't look like an optimization problem. I haven't defined an objective function for you. But can I apply the idea of optimization to solving this problem? And if so, how should I think about it? Okay, so one idea, example 1 would be, if I define my objective function as this. Seems like a good idea, right? Because when this is minimized, Ax is going to be equal to B. Okay, any other idea? Okay, that's example number 2. So he's saying phi x is equal to 1 by 2 x transpose Ax minus B transpose x. That is also correct. Why is this correct? Right, when I take the gradient of this expression, what will I get? Right, so if I do grad phi of x, I'm going to get Ax minus B, and we know that when we are in an optimization problem, we are looking for a stationary point. A stationary point is defined as a point where grad f x is equal to the 0 vector, right? So when so this is the so which of these two ideas is going to be better? They both on the face of it are perfectly legitimate ideas, right? Now which should we choose, example 1 or example 2? In example 1, if I open this up, what am I going to get? Norm something squared, for example, would be Ax minus B transpose multiplied by Ax minus B. What is going to be the term that involves the quadratic term? What will it have? What will be the expression? X transpose, A transpose, Ax. It's going to be X transpose, A transpose, Ax, and 3 more terms. Okay. I am focusing only on the quadratic term. Why do you think I'm doing that? A transpose A is symmetric, it is positive semi-definite at least. We don't know about the eigenvalues. So from this point of view, can someone say which is better? So let's call this phi 1x and phi 2x. Let's assume A is invertible. Okay, one answer is that it doesn't matter, both are the same. So the hint is to look back at the rate of convergence that we had discussed in a previous module. What did that rate of we didn't derive the full expression, but we gave an expression. What was the essential quality of this, the matrix that is sitting inside that comes into picture? Condition number, right? So in case of phi 1, the matrix is A transpose A. In phi 2, matrix was that I am working with was simply A. Okay. Now better the condition, higher the condition number, is it good for us or worse for us in terms of convergence? Worse, right? So higher is kappa, worse is progress. Progress is one thing, another thing is the higher the condition number, as you saw from the tutorial problem, accuracy is also questionable, right? If there is an error in the B vector, your solution is less accurate. So worse is the progress and the accuracy. All right. Now let us say the matrix A has condition number kappa. What is the condition number of A transpose A? It's kappa squared. Right? It's simple eigenvalue decomposition. You stick A transpose A together, you will get the square of the two diagonal matrices will multiply with each other, all the eigenvalues will get squared. Therefore, the condition number is largest eigenvalue to smallest eigenvalue. So, this becomes kappa squared. Did everyone follow this? Right? Just write down the eigenvalue decomposition for A, then A transpose multiply to get squared. Kappa is a number that is greater than 1 or less than 1? Greater than 1, right? So, that is why this method is less preferable. It will give the correct answer, but the moment you enter the real world where there is error and noise, the noise is going to get amplified by a square of condition number, rather than second approach where you are working just with condition number, right? Yeah. Yes, yes, correct, correct. Excellent, right? So that's a very good point. You have beaten me to it. Let's put over here. So A can be anything, whereas in the second approach, A has to be positive definite, or as we have learned, symmetric positive definite. So A has to be positive. Right? So if you were dealing with a very general purpose problem, you may have no choice. You may have to go for approach 1 and pay the price of condition number. But as we will see, there are lots of tricks around these things, right? But if your matrix was given to be positive definite, you should definitely go for approach 2 because your condition number is better. Okay. So in what follows, we will now make, because we want to study the essential core idea of conjugate gradient, we are going to make our life easy. We will say assume A is symmetric positive definite. Okay, so here on, assume A is symmetric positive definite. Okay. And as we have already seen, the cost function that we are going to assume is half of x transpose Ax minus b transpose x, which leads to a common shorthand, instead of grad fx, a common way to call this term Ax minus b is Rx, which simply stands for the remainder, right? Ideally, we want the remainder or residual to go to 0. So another way in which this variable is kept track of is Rx, okay, which is the residual. Okay, now given the fact that we are working with a symmetric positive definite matrix, there are some nice properties of this matrix that we know of. So we'll just quickly summarize those 2-3 properties. We'll use them throughout the method. They're very crucial. It's also again like a small revision of linear algebra. Okay, so A is symmetric positive definite. Therefore, if I write its eigenvalue decomposition, that's how it's going to look, right? The columns of U are what? Eigenvectors, right? So the columns are eigenvectors and lambda is a diagonal matrix of eigenvalues. Right? Sometimes we tend to forget, is it U lambda U transpose or U transpose lambda U? What's the quick way of figuring it out? Which one is which, if you don't want to rely on memory? These are small hacks which you should build in. Huh? Correct. So you know, when anyone says eigenvalue problem, what is the first thing that even in class 11 you study Ax equal to lambda x. Everyone knows that, right? So if I were to multiply from the right by u, what will I get? I'll get u lambda, u transpose u. Now u consists of orthogonal columns. This is a property of positive definite matrices that the eigenvectors are orthogonal to each other, right? And in fact, you can orthonormalize them also. So this becomes what? Identity. Now u right multiplied by a diagonal matrix, what will happen? The lambdas will multiply each of the columns, right? So lambda 1, this will become like u1 lambda 1, u2 lambda 2 dot dot dot. This is how it becomes. And so u is already there, a into u. So you can see that if I take u1, u2, un, so you can see now this there are n eigenvalue equations here, right? A u1 is equal to lambda 1 u1. That's your eigenvalue problem, right? So that's a very quick way of just getting it right, that it's u lambda u transpose and not the other way around. Okay. All right, this has given us one property I've already stated, which was that u transpose is the same as u inverse. Okay. Is it easy to see this? Right, u's, if I take u, the columns are all orthogonal, right? So if I take u like this as columns, right, and if I take u transpose, this is u transpose over here, all those guys become rows. Now when I multiply u transpose into u, what will I get? Since they are orthonormal to each other, right, I'm only going to get diagonal terms in this, right? So this is going to give me diagonal. In fact, since they are orthonormal, what will this be? Identity, right? So this shows you, and it's a square matrix, of course, right? We are working only with square matrices. So this gives you u transpose is equal to u inverse, quite straightforward. This U matrix has a few more nice interpretations. For example, what does it do to the length of a vector? Supposing I multiply U multiplied by some vector Q, okay, and take the length of that vector and compare it to the length of the original vector itself. What happens? It's equal, right? It's actually equal. So that gives us, the reason I state this is because it gives us a nice geometrical interpretation. In n dimensions, what's going on? It's a rotation. I take a vector, multiply by u, it just rotates it. Rotation does not change length, right? So you can write this algebraically like this, does not have much intuition, but now you see, okay, it's actually just a rotation, right? So it's length preserving. It's length preserving, but now what about if I have two vectors, let us say q and t, and I apply u to both of them, will it change the angle between them? If it's a rotation, it should not change the angle between them, right? So that's the second property. If I do uq and ut, so this is the inner product, it should be the same as the inner product of q and t. You would have seen the proofs of all of these in linear algebra. They're quite straightforward.